Morning, students. In today's session, we will deal with the concept of process synchronization. So, at the very beginning, we have to uh, know about cooperating processes. So, basically, what is a cooperating process? A cooperating process is one that can affect or it can be affected other processes executing in a particular system. So basically, cooperating processes may either directly share a logical address space, such as both code and data, or it can be allowed to share only data through some files. So the former case is basically achieved through the use of lightweight process or threads that we have covered earlier. So now concurrent access to shared data, it may result in some sort of inconsistency. So for that reason, in case of cooperating processes, process synchronization is essential. So here you can say that in a particular operating system, there are several processes which have been running, and some of them may like to share resources with each other, and in doing so it may lead to some sort of inconsistent state. Take an example here that one process is changing the data in a memory location and another process is trying to read the same data at the same point of time from a memory location. Then what will happen? So that means when updation is going on, another entity can try to access that data, and definitely it will cause some sort of error here. So in the diagram which is shown on the screen at this point, you can see there are two processes, process A and process B. So process A is writing something on the shared data, and process B is trying to read those data. So in such a scenario, if there is not certain kind of synchronization input into practice, then it may give some inconsistency in the output result. So basically, let's take an example here. Produce as a very simple producer-consumer problem. So we are considering that a buffer is being given here. Buffer means some sort of temporary storage where the producer is putting some item, and the consumer process is there. Consumer is consuming the items from that particular buffer one by one. So basically, what can be the problem here? That the producer should not add data when the buffer is full. That means the consumer is yet to consume the data, and and at the same time, the consumer should not take anything when the buffer is empty, because when the buffer is empty, there is nothing to consume. So in that case, such problems may arise. Now, regarding producer-consumer problem, we can say that a particular process produces information that is consumed by the consumer process. For example, say a print program is producing some characters that are being consumed by the printer driver, and for the consumer's point of view, say a compiler may produce some assembly code which is being consumed by an assembler. So in this way, the producer consumer problem program, they are two separate entities. They may be running in isolation, then there is no problem. But if they are modifying some common data structure, then only the problems can arise. Okay, and to avoid that problems, we have to synchronize the activities of these two processes in some manner. So basically, we will look into these aspects throughout this session and the upcoming sessions that we will execute. So going to the next slide. Now, what can be some possible solution to producer-consumer problem? We can use the concept of semaphores. What is semaphore in computer science? Particularly in operating systems, a semaphore is nothing but a variable or an abstract data type that is used for controlling access by multiple processes to a common resource in a concurrent system, such as a multi-programming operating system. That means In case of multi-programming operating systems where there are multiple processes being running at the same time, and when they are trying to access a common data structure, then using the concept of semaphores, which is nothing but a variable or an abstract data type, we can control the access of the particular common data structure by the competing processes. There are some other mechanisms also for implementing several solutions to the producer-consumer problem, but using semaphore we can do pretty easily. It's a very common, popular technique. Now, let us consider a particular situation where the producer and the consumer processes are being shown here. There are three lines of code here as a part of producer process and as a part of consumer process. We will examine those instructions now. Basically, from the example shown in the slide, you can easily make out that what are the particular operations that are being carried out here. So basically, some sort of counter variable is there, and you are storing the value of the counter in a register called register 1 here, and then you are incrementing the value of register by 1 unit, and again you are putting the update value in the counter. And for the consumer process, basically the same thing, but in case of consumer process, you are decrementing the value of the counter variable by 1 unit. So basically, it is nothing but a simple incrementation and decrementation operation with a variable here. That variable is is called the counter variable. That means counter variable is a common variable. In both the processes, you are been working with the counter variable. Now see what sort of problem here can arise here. So as an illustration purpose, suppose the value of the variable counter is actually 5 at a certain point of time, and the producer and the consumer processes execute the statements counter plus plus and counter minus minus concurrently. So basically, just I told you now that basically here we are incrementing and decrementing the counter variable by 1 unit, and these processes, these instructions are being carried out concurrently. Now, following the execution of these two statements, what can happen? The variable counter value may be either 4 or 5 or 6, but only the correct result is counter equal to 5, which is generated only if the producer and the consumer processes execute totally separately, but that is not the case. Now these two processes are intermingling, they are trying to execute concurrently, and in doing so some problems can arise. So what can be the problem? Just come to the concluding part here. Suppose at a particular point of time t0, the producer is executing register 1 equal to counter. So now register 1 will be having the value as 5 here. So we are assuming that at the very beginning the value of the variable counter is 5. So then at time instant t1, producer process again execute register 1 equal to register 1 plus 1. That means the value of register 1 is being incremented by 1 unit. That means register 1 now contains 6. Now, at time instant t2, the producer is interrupted and the consumer process comes into play. So the consumer executing register 2 equal to counter. That means now the previous value of counter was 5. So register 2 gets the value 5 now. At time t3, consumer executing register 2 equal to register minus 1. That means register 2 ultimately contains the value 4. Now at time t4, what happens? The producer is executing the instruction counter equal to register 1. Now register 1 was earlier 6. That means now counter will be carrying the value equal to 6 now. And at time t5, the consumer is executing counter equal to register 2. Now the earlier value of register 2 was 5 there. It was decremented. So now the counter will be containing the value counter equal to 4 now. That means uh, from the last two instructions, you are getting the value of counter as 6 or 4. but not 5, which is the actual value of the counter. Now, just if you change the order of T5 and T4, then what will happen? Then again the same thing. That means the value of the counter will not reflect the actual correct value, which is 5. So those issues are happening here. Now, why these issues are happening? Because we are allowing both the producer process and the consumer process to access the counter variable simultaneously. That's why these problems are happening. So if we can control the access of the two processes separately, then those issues will not happen. So such a condition is called a race condition. So basically in race condition, several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place. So such a condition is called a race condition. Now to avoid the race condition, we need some sort of process synchronization among the concurrent processes. So that is the thing here. Now basically, when there are several multiple processes trying to execute concurrently, and when they are trying to update a common variable, so in that case, each of those separate programs or processes, they contain a certain section of code which is called critical section, and in that critical section only the process tries to modify or update that common data structure. That means a section of code common to n cooperating processes in which the processes may be accessing common variables. Now here, whenever a particular process tries to access the common variable, it must be executing in its critical section. We are calling that particular section of code as the critical section. So basically, the critical section is being identified by, say, 4 sections here: entry section, where the code requesting entry to the critical section is being implemented; critical section where the code in which only one process can execute at any one time. That means if there are n processes, only one of the particular process should be allowed enter into its critical section at a particular point of time. Exit section, that means the end of the critical section, releasing or allowing others in the remainder section, that is the rest of the code after the critical section. That means basically we are separating our code into 3 or 4 sections here: entry section, critical section. And after executing in the critical section, the particular process goes into the exit section, and after the exit section, the remainder section is there where the rest of the activities are being performed. So so basically, the critical section, to prevent inconsistencies from creeping in, the critical section must enforce all 3 of the following rules. What are those rules? Those rules, number 1 is mutual exclusion. That means no more than one process can execute in its critical section at one time. That means if there are n processes, only any one of those n processes may be executing in its critical section at a certain point of time. Next is progress. What is that? If no one is in the critical section and someone wants to get in, then those processes not in that remainder section must be able to decide in a finite amount of time who should go in. That means if someone wants to enter into the critical section, then it should be allowed to do so, and that will be decided upon by the remaining processes which are not working in the remainder section. So that is the thing. And lastly is the bounded wait. What is that? All the requesters must eventually be let into the critical section. That means a process cannot be waiting indefinitely to get into the critical section. That means there should be some sort of movement that must be allowed. That means the concept of starvation should not happen. If somebody is requesting to get into the critical section, then it must be allowed to go into the critical section. There is a particular bounded waiting time is there. So within that time, it should be definitely allowed to go into the critical section. So that is all about the critical section. So in the next slides, we will move with the concepts of process synchronization in more depth. So with that, we will be closing here. So thank you